14 a little bit quicker than we did. So that's probably why. I just didn't realize she was that far ahead. So I'll talk to her today because we are doing a meeting today.
'Cause I figured that she does like Tuesdays and Thursdays or something.
Yeah, she does Tuesday, Wednesday, Thursday.
Oh, okay.
And we are
Okay, yeah.
one session behind because we skipped a session last week. So that's a little bit it as well. But yeah. We're going to go a little bit faster just because I don't want to be like super behind or anything. But do you guys know when your exam is by chance? I know it's in November, like the 2nd.
It's in 2 weeks.
2 weeks?
So not next week, but the following.
Okay, cool. That's what I thought. So it's either the 12th or the 13th, depending on what class you're in. And I believe the exam should only be chapter 14 and 15. So that's why I wasn't planning on going over 16, but I will check on that and let you guys know, because now I'm kind of concerned.
Depending on like if 16's a lot, I mean, I feel like I have enough time just to like prepare. Since like next week I could just be doing 16 and this week is like 15.
Mm-hmm. That's a good point. I'll look into it and I will let you guys know what like the schedule is set to be, and then we can work from there. Cool?
All right.
Oh, it just occurred to me I'm not sharing my screen. Oops. Okay, so you guys were saying go over chapter 14 problems, go over directing effects and that kind of stuff, and then some chapter 15 problems. So yes, we can. I'm going to say let's do a little bit of 15 first and then go back into 14. And please tell me which ones in like particular you would like to do for 14, and then we can totally do that. Let's say at 11, like 35, we go back to chapter 14. That'll be my plan. Let's hope I remember. So for 15, I feel like most of you guys are my regular tutoring students, so you guys were here on Wednesday. So this is what we did Wednesday. If you weren't here or anything, we essentially just started on directing effects, and pretty much I explained the concepts of an activator versus a deactivator, where an activator is just a group that is going to make the benzene ring more reactive, and a deactivator is just going to make it less reactive. And so in our electrophilic aromatic substitutions, we want our benzene ring to have as much electron density as possible because it is going to be the nucleophile. And so as we knew from chapter 13, electron donating groups make the nucleophile more nucleophilic versus the electron withdrawing groups make the electrophile more electrophilic. So electron donating groups are really, really good for the benzene ring. They make it really reactive. Electron withdrawing groups deactivate it and make it less reactive. And then we went on to these resonance type problems, and we did sorry, I got distracted by the chat. Someone said which is more nucleophilic. So up here, the electron donating groups would make it more nucleophilic, and being more nucleophilic just means that you have more electron density and you're more likely to attack things. Did that answer your question? Yes. Okay, cool. You are very welcome. So we did the resonance structures for phenol, which is the first one. And I showed you guys the resonance structures for something like the second one, but we're going to just do it again today because I like ran through it really quick. So in the last example we looked at, it was just a regular old carbonyl, but now it's something more complicated looking. So we're going to move that double bond up. And so create a double bond here, and that would kick this double bond, or yeah, that double bond up. So now you have two negative charges, which is not good because overall you want a 0 charge. So we see that this nitrogen will still have a plus charge, and we have to have another plus charge somewhere else in the ring. And we knew that the electrons that were here are now gone, so we replace that with a positive charge. And now this just keeps happening in a circle. So these electrons are going to go here to try and balance out that positive. And just for simplicity, I'm not going to draw the electrons here every time. But here we have two double bonds in the ring again. And the plus charge is now where compared to our substituent group? What position is it on? Para, exactly. Cool. So now going on to the next step, we will have these electrons come here. So bam, bam. That was a terrible line, but we're going to leave it. Now our plus charge is on what position? Ortho. Cool. So at this point, we've pretty much gone through all the resonance structures, or I'll draw the last one just for completeness. So in the last one, this would go here, right? And then, actually, I'm not going to draw that just because that becomes confusing then, because this is the only one we care about. Forget what I said before. Technically, there are more resonance structures, but as far as this goes, I only want to show you these because then it gets complicated. So, the main difference between the top one and the bottom one is not where the charges are, but what the charges are. So on top here, we have a negative charge on the ortho and para positions. And then down here, we have a plus charge on the ortho and para positions. So it will end up being a delta plus, delta plus, delta plus. And the way this affects our ortho and para positions is that now they are more electrophilic. So by default, these meta positions are actually going to be the better the better nucleophiles. So when we talk about directing effects, groups such as this one, which are electron withdrawing, are going to direct to the meta position. Versus groups like this that are donating are going to direct ortho and para because those are the most nucleophilic carbons.
I'm sorry. Could you repeat that one more time?
Yes,
for the nitrogen.
Yeah. So basically, up here we saw that there was a negative charge on ortho and para. And here we have a positive charge on ortho and para positions. And so instead of these positions being more nucleophilic, they're going to be more electrophilic. Which means that a group like this one will be meta-directing because in comparison to these positive charges, this is the most nucleophilic center. I can say it again if you want. I know it's a lot.
Yeah, because I'm trying to understand. Like you saying the meta the nucleophilic center. So I thought nucleophile was like negative. My bad.
Yeah, exactly. So here it's really easy to see like, oh, this is negative, right? So that means that's the nucleophilic center.
Yeah.
But here we don't have any negatives. We just have positives. So that's why this overall is going to be less reactive, right? Because remember up here we talked about withdrawing groups, they're deactivators. And so as we can see, this one overall is going to be kind of shitty, right? Because this has all that negative, but this one has all the positive.
Oh, so you're saying the meta position is the better nucleophile because the P and the ortho have positive?
Perfect.
Okay, now I get it. Thank you.
You're welcome. So overall, the whole ring is less reactive, but because there's a positive on the ortho and para positions, the meta is going to be more nucleophilic.
Thanks. You explained it really well.
You're very welcome. I tried. And then someone said, so it can still react despite having an electron withdrawing group. Yes, it can still react, but it's just going to be a lot less likely to react. So if I gave you both of these benzene rings and said which one is most likely to react again, you would say this because this one sucks. It can, but it sucks. You're very welcome. Okay. And so this is just something we did last time. It's not important to what we're going to talk about, so I'm going to delete it. This list is one that I believe I got directly from Dr. West and his PowerPoint. And we talked about general activators and deactivators, and like different rules, like positive charges are withdrawing groups, negative charges are donating groups. But for this chapter, you actually have to know more in depth than that. So I gave you a list of all of the substituents you have to know for this chapter. And you don't have to know each one like, this is number 1, this is number 2, this is number 3. You just have to know general trends. And so I went in and color-coded these for you guys to make it like easier to see. But I'm just going to go ahead and put lines here. And we're going to put these into different categories. So I already have the answers written there for you guys. But these are all what kind of groups? Donating, exactly. And they're all donating groups because we can see that they all have lone pairs here. And can anyone tell me what functional group this is?
Is it ether? Yeah.
Yes, right. It is an ether. Cool. Just making sure. What if I gave you this functional group? What's this one?
Oh yeah, ester.
Ester. Cool. Exactly. Cool. Just making sure we still got those down. All right. And then so X stands for what?
Halogen.
Cool. All right. So yeah, that's all you guys really have to know the names of. So as we can see, these are all electron donating groups. But these are all electron withdrawing groups, but they were split into 2 categories, or 2 groups. And it's very important to note that halogens are going to be in their own group, and all the rest of the deactivators are going to be in their own group. So we can go ahead and say, I'll make that line better, that halogens are weak deactivators, and the rest of these are strong deactivators. Wow, I don't know why it looks like 2 separate words here. And when we look at our activators, they're all in one group. So there's really no need to separate it. But as we learned in chapter 13, which one of these is considered a weak activator or a weak electron donating group? R groups, exactly. So we can still think logically that these are still weak donating groups, but they're not technically part of a different category. So all of these are electron donating, and these are electron withdrawing.
Wait, so you said R groups are weak electron donating groups?
Yes. They are weak donating groups, but they don't have their own category. So just think of them as being the weakest activators. Okay. And so the last thing I kind of logically want to tell you guys is we talked about what an orthopara versus meta director is, and then what an activator versus a deactivator is. And so now we're going to put that together. And someone said, can I repeat that? I don't remember exactly what I said, but essentially I think it was about R groups. So R groups are going to be our weakest activator. I think that's what I said. Maybe. I don't know. Let me know if that was it or not.
I have a question.
Mm-hmm.
The ones on the left side, those are your weak activators or your strong deactivators? Activators.
So all of these are going to be your activators, and it pretty much goes in order from strongest to weakest.
Oh, okay. Thank you.
You're very welcome. So, yes. So I know I've harped on this a bit, but a lot of people tend to be confused. So orthopara is the directing effect, and that comes from resonance pushing the delta minus on the ortho and para positions. Same goes for here. And being a meta director just means that because of resonance, you have a positive charge on ortho and para, which makes the meta position most reactive. And activator just means that overall the ring becomes activated. Deactivator just means overall the ring becomes deactivated.
So to repeat, you said the meta position, when the meta position is the most reactive, just means that ortho and para are positive.
Yes, exactly. So now, the reason I say that so much is because we have to put this in order of most to least reactive, and that's kind of how I put them to begin with. And he kind of is a little bit confusing when he talks about this in lecture, only because he uses most reactive, least reactive, activator, deactivator kind of all interchangeably, and then it kind of confuses things a bit. So even though this is a deactivator, we can say that this is more active or more reactive than this one. And even though these are all activators, we can say that this is more activating and this is the least activating within that group. So when I say things like that, if you have any questions, just let me know. That's pretty much it for this list. For the most part, you kind of just have to memorize it. But you can know concepts like NH2 versus OH or OR groups. The nitrogen is going to be the most donating group because, remember, between nitrogen and oxygen, which one is more electronegative? Oxygen, exactly. So the more electronegative, the less it wants to donate. So nitrogen is really important. You have to know that this is the most activating thing we can have on a ring. And then OH and OR are pretty much the same. Just know that that's next. And then these two are pretty much the same as one another. Just know that they're next. And then you know that R groups are the least activating of the activators. And then just know this is all by itself. And then these are kind of important that you know the order of. So all the carbonyls are going to be like the weakest deactivators. And then NO2 is going to be the strongest deactivator. That's important to know. And why do you think that this could be such a strong deactivator? And guesses are totally valid. There's 2 oxygens, true. Also, if I draw this out, aren't there charges? Yes, exactly. So there's a plus charge on the nitrogen. So we have all that electronegative stuff going on, plus we have a plus charge. So that is going to be super, super deactivating.
Wait, so for the NH2, that one would be the most reactive because it has 2 hydrogens? Or no? I mean, electro donating.
Sorry, what was that?
I meant to say electro donating.
Yeah, exactly. So it's the most electron donating. That's why it's the most reactive.
Is it because it has 2 hydrogens? Or
not necessarily because of the 2 hydrogens. It's mostly just because nitrogen itself is really donating, and it donates those lone pairs versus oxygen and like something like this would have less of an inclination to donate electrons because they're more electronegative.
Okay, thanks.
You're welcome. Okay. So we've gone over like conceptual stuff. Do you guys want to do an actual question about donating effects and stuff? Yes? Okay, sweet. So these are actually really fun. I really like them. So let's say we have this, right? We have our substituent right here. Is it a donating group or a withdrawing group? Donating group, cool. So do we think this is ortho-para directing or is it meta-directing? Ortho-para, cool. So it's an ortho-para director. And is it an activator or a deactivator? You can just say A or D. A, exactly. Sorry, guys. So it's an ortho-para activator. So that means that this position, and this one are going to be the most reactive. And so our next group is going to be added to one of those positions. So if we have Br2 and FeBr3, what is being added to the ring? Bromine, exactly. That's so ugly, but I'm going to resist the urge to redraw it. So this was our original substituent, and we can actually have multiple products. So we could either have the bromine added to the ortho position or to the para position. And I'm just going to write underneath, this is the ortho product, and this is the para product. Technically, we also have another ortho product added to this side, but it's exactly the same molecule, so I'm not going to bother drawing it out. I don't know if you guys can hear Bear crying to be let in. What a weirdo. Any questions on this one?
Yeah, what made you think it was ortho para directed right from the beginning?
So, one, because it's a donating group. So we know that all of the donating groups are going to be ortho para directing. And also, if we think about activators versus deactivators, we know that all the donating groups are activators, and we know that all of our activators have to be ortho para directing. Cool. Okay, so for this next one, what do we think? Ortho para or meta? Meta, and cool. Why do we think that? It's a deactivator, cool, but now deactivators have two groups. We have strong deactivators or we have weak deactivators. Yes, exactly. It's a strong deactivator. The only weak deactivators we have are halogens, and we also know that this is a meta director. And more specifically, this was one of the three groups I told you guys were super, super important. What did I say was important about this one? Yes, it is the strongest deactivator. Cool. Just making sure you guys are listening. So SO3 plus H2SO4, what are we adding to our benzene? Someone said SO3. That's the trick they always do. SO3 is the group that's given here, but what is actually added to the benzene ring? SO2 closer. SO4. No. Okay, let's zoom up here for a second. Where'd it go? I lied. Hold on.
Is it SO2H or SOH something?
SO3H, but I just wanted to show you guys again the nitration and the sulfonation. Very, very, very important because they will for sure trick you by giving you just SO3 added or giving you SO2H. So just remember, for nitration, they give you HNO3, but you only add NO2. For sulfonation, they give you SO3, but you add SO3H. Okay, cool. Can I close it? Any questions?
No, a quick question. I know you're probably already answered this, but how would I know if it's on the meta? One more time, or should I just memorize that if it's in that position on the top? And
Oh, for the actual meta and ortho positions, or just
no, I'm talking about where the NO2 is how would I know that's automatically meta?
Okay, so this itself doesn't have an ortho meta para thing, if that's what you're talking about. So
Yeah.
NO2 is just there. There's only one group, so it's just there. There's no ortho meta or para to it yet. What is considered meta to this is this position right here.
Oh.
Yeah, and when we say meta, all we're saying is that on this list up here, it was one of the meta directors, right? And then if we went here, all that means is that ortho and para are positively charged, so the meta position is the most active.
Thank you.
You're very welcome. And then someone said if it's a deactivator, it's meta, except in the case of a halogen. Because a halogen is a deactivator, but it's orthopara. So almost always, except in the case of a halogen. Someone asked, could there be ortho, para, or meta in a benzene with multiple substituents? We're going to look at that actually later in SI or whatever. You would have two separate sets of ortho, para, and meta for each substituent. And then you would go from there. Okay. So in this case, we are adding an SO3H. And we have two possible answers again because we have two meta positions, but they're going to be exactly the same. So I'm only going to draw one answer. And it will look like this. You could have also drawn it on the other side, doesn't matter.
For these types of questions, could he ask you, like, what is the ortho product or what is the para product instead of, like, asking for both?
He could, he could give you this and say, which of the following answers is the ortho product, and you would just have to know that ortho is right next door. But if he were to just say, like, which of the following is a product, both of them are the answer. So he could ask you both ways, but he's more likely to say, like, ask for all of the answers, if that makes sense.
Yeah, like, could he only put one of the products as an answer, though?
Oh, yeah. Like, if he didn't specify ortho in the question, could he just give you the ortho product, you're saying?
Yeah.
He could, but he wouldn't ask, like, what are all of the products? He would say, like, which is one of the possible products.
Oh, okay. That makes sense.
Cool. So, as I promised, we could go back to chapter 14. Do you guys have any questions about this stuff before we go on, though? Because we covered a lot. It doesn't seem like it, but it was a lot. You're very welcome. Felt that. Okay, cool. So, oh, actually, I lied. I want to just talk about one quick thing. So, what reaction is this? Please remind me. Friedel-Crafts, exactly. So, and yes, it's the alkylation. Cool. So, all right. And the important part of this, the reason why I'm talking about it is because Friedel-Crafts is super, super important. Because it doesn't work with NH2 or any strong deactivators. So, if we go back up to this list, Friedel-Crafts will only work for these. If we have this on a benzene ring or these on a benzene ring, the Friedel-Crafts reaction will not happen. Cool. Any questions?
So if you get a deactivator that's meta, would it like be no reaction because it can't react to that one?
Exactly. So if I gave you, let's say, Can you just, thank you. Sure. If I gave you this, the answer would be no reaction, because as you said, it can't work with a strong deactivator. And yes, for acylation as well.
Okay, thank you.
You're very welcome.
So it doesn't work for a strong activator and deactivator like the NH?
So yes, I don't want to say strong activators because technically speaking, all of these are strong activators, but for the strongest activator and for any strong deactivators.
Thanks.
You're very welcome. Okay, so let's look here. Did I include? No, I didn't. Sorry for all the scrolling. Alrighty, so which questions do you guys want to go over?
Could we go over the 3 on the bottom, like to the right?
Yes, these 3?
Yeah.
Yes, of course we can. So, for this one, is it I didn't just drop that. Is it cyclic, planar, and fully conjugated? Yes? Okay, cool, exactly. And so now let's go ahead and count how many pi electrons we have. So 2, 4, 6, 8, 10. Because we know it's 2 per double bond. So 10 pi electrons. So 10 pi electrons, does that follow the 4n rule or the 4n plus 2 rule? 4n plus 2, exactly. So would that make it aromatic or anti-aromatic? Aromatic, cool. So the next one is super similar, but now we have an oxygen. And I'm only going to draw out one lone pair of the oxygen because we know only up to one lone pair can count, right? So, can we tell if this is cyclic, planar, and fully conjugated yet? Yes. Can we assume oxygen is sp2? I mean, maybe you can see it and already think of it, which is cool, but and it's really good. But if you can't, let's go ahead and decide sp2 versus sp3. So if it's sp3, we know that it has to be non-aromatic. But if it's sp2, how many pi electrons do we have? Eight. No, I lied. 10. Because we have 2, 4, 6, 8, plus 2 from the oxygen. So that would make 10 pi electrons. Because remember, if we count it as sp2, then it has to donate one lone pair of electrons. Does that make sense? How I counted? Yes? Okay, cool. So then if there's 10 pi electrons, is this aromatic or anti-aromatic? Aromatic. So between aromatic and non-aromatic, which one are we going to prefer? Aromatic. Cool. Yay. So then next up, very, very similar, but now we have boron. So now can we look at this and automatically know whether boron is sp2 or sp3? Yes, because it's always sp2 and it always has how many electrons to donate? 0, exactly. So this is cyclic, planar, and fully conjugated, but how many pi electrons do we have? 8, exactly. So that would make it anti-aromatic. And since it has to be sp2, we don't get to choose. Any questions on those three? No? Okay, cool. Do you want to do any more of these?
I have a question about his practice problems.
Yes.
So for chapter 14, like the questions kind of ask at the beginning like names of like the benzenes.
Oh yeah, we can run through that real quick because I forgot to do that when we did the list.
Okay. Or unless we're going over an SI.
We probably will go over it in SI unless my brain turns into like wax and melts. But I should be going over it today.
Okay.
Okay. And then someone asked for this example. So yes, we can go over it. First of all, is it cyclic, planar, and fully conjugated? And I'll make these a little bit more obvious. Yes, because we know that radicals are sp2. So since this is cyclic, planar, fully conjugated, we know it has to be either aromatic or anti-aromatic so far. And so if we count 2, 4, 5, 6, 6 pi electrons, does that follow the aromatic or anti-aromatic rule? Aromatic. Cool. And yes, we can do this one. I just want to... I don't know if I have an example like this one. 1, 2, 3, 4. Yes, I do. Okay. We're going to do this one right above it. Because it's cyclic, planar, and fully conjugated, right? But how many pi electrons do we have? 5. And so 5 pi electrons means it has to be what? Non-aromatic. Exactly. So if you only have one radical, it's pretty much always going to be non-aromatic. Just remember that. So for lone pairs, would we be able to see whether it's sp2 or sp3 like we would for heteroatoms? So for lone pairs, not necessarily. So that p orbital can have 3 states. It can either be a plus, a radical, or a minus charge. And so it's always going to be sp2. And you're only allowed to count the number of electrons you have based on the charge. Does that make sense-ish? You're very welcome. Okay, so let's do this lovely one. So we have to figure out sulfur and oxygen, and each of them can have max 1 lone pair donated. So I'm going to draw 1 lone pair for each. And remember, they have to have the same hybridization. So they can either both be sp2 or they can both be sp3. And if they're sp3, we know it's going to be non-aromatic, right? And so let's count up how many electrons we would have if it was sp2. So we have 2, 4, 5, 6, 7, 8. And we know that this gives us no electrons. So if we have 8 pi electrons, will that be aromatic or anti-aromatic? Anti, yep. So between anti and non-aromatic, which one is preferred? Non-aromatic. Ta-da. They look really terrible, but once you take like the main rules and kind of orient yourself, they're not too bad usually. You're very welcome. Any more of these? We have time for like 2 more, or we can just review everything we did today. The cyclooctane ones. Yes. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so these 2? Yes. Okay, so let's pretend that never happened. Okay. So cyclooctanes are the ones where we have to figure out whether or not it's going to be planar, right? Because 8 or more membered rings have that pesky planar problem. And so now we're going to treat it just like we did with the oxygens, where we decided whether it was sp2 or sp3. So planar, non-planar. If it's planar, it will be cyclic, planar, fully conjugated, and it will have how many pi electrons? One person said it. Okay, cool. So yes, it will have 8 pi electrons, and it has 8 pi electrons either way, so I'm not going to write it under planar. But if it has 8 pi electrons and it remains planar, that will be what? Aromatic or anti-aromatic? Anti. And if it's non-planar, it's always going to be non-aromatic. So is it more favorable for this to stay on the plane or to bend out of the plane? Bend out, exactly. So it will be non-planar and it will be non-aromatic. But we can manipulate that, right? Because here we have the same size ring, but now we have how many pi electrons? 6. So we have 6 pi electrons. If it's going to be planar, it would be what? Aromatic or anti-aromatic? Aromatic. And if it's non-planar, it's always going to be non-aromatic. So usually, this, I didn't drop it again. So usually a ring like this is strained. It doesn't want to be on the plane. But if it can stay on the plane and endure that ring strain and have aromaticity, that is totally more favored. So it's going to stay on the plane and it will be aromatic.
I think I'm a little bit confused on how you're determining whether it's anti-aromatic from if it's planar or not.
Great question. So we're not necessarily doing from whether it's planar or not. We're just saying like this ring itself would be anti-aromatic given that it was planar, right? Because of the 8 pi electron rule. But
So I think it's non-planar is going to be non-aromatic, basically.
yeah, exactly.
Gotcha.
Cool. Any other questions? Do these 2 make sense? I know the planar rule is kind of weird. The planarity rule. I can zoom out if you guys want to take a look at the whole thing. Questions, comments, concerns? I was playing Halloween music in the background. Could you guys even hear that? I feel like you can't. Nope. Okay, cool. How about now? No. That's fine.
What are you doing for Halloween?
What was that?
What are you gonna do for Halloween, and what are you gonna be?
Oh, so unfortunately, I can't dress up this year just because I have too much stuff going on. But I do have a Spider-Man onesie and a Totoro onesie. So I think I'm going to be Totoro, and I'm going to do a Halloween movie marathon in my bed with some hot chocolates.
Oh, that's cool. That's cool.
How about you guys?
I mean, with like COVID and all that, probably I'm just gonna stay in and like study this stuff.
Spook you need to do on Halloween, truly. Last semester, someone was like, I was studying and all I could hear was you screaming in my head. And I was like, that is spooky. Happy Halloween. Ooh, studying for microbiome. That sounds awful. I've never taken microbiome, but I've heard it's like the worst class.